My name's Varun, and I'm here with my colleague Dhawal to talk about OCP attestation and how we've implemented it on NVIDIA Silicon. In collaboration, these slides are made with our colleague James, who couldn't be here today. Start with an introduction. What is attestation? Attestation, as defined in OCP attestation, is a way for a device to make trustworthy claims about its configuration, what's running on the device. And that leverages a concept called measurements. So an example is a device implementing an active component root of trust would measure the things that are running or the configuration that it has, and then cryptographically sign it, report an attestation report. This device is acting as a tester. That attester is sending the attestation report to a verifier, which then checks whether those claims are valid and expected for that configuration. And then if they are, gives privilege to a relying party so that that relying party can then use the tested device in their application. Why do we care about attestation? NVIDIA is not only known as a GPU manufacturer, but also as a server manufacturer. And what we care about on our servers is the integrity, authenticity of our firmware. And so by using attestation, we're able to collect claims from all the devices on our servers and make sure that they're configured correctly. Most recently, we've also launched a GPU product called H100 that features an initiative called confidential computing. And with confidential computing, a confidential VM is able to gather an attestation report from a confidential GPU. And then if that GPU is running the expected firmware and driver software, can establish an encrypted session with that GPU and then pass data back and forth. OCP attestation was crucial for us in terms of defining our attestation flows across both the server and confidential computing domains. The OCP attestation spec introduced provisioning, platform components, the concept of a protocol, and what to measure. In particular, for this talk, we're going to focus on the keys and provisioning. OCP attestation introduced the concept of an identity key, which is immutable for a given device, and an attestation key that chains that identity key. The attestation key is responsible for actually signing the attestation report that's used to provide the claims. On the right-hand side, you see a certificate chain that comes from the SPDM 1.2 specification. And there you can see at the top, there's the root certificate authority, intermediate certificate authority. These are provided by either the device manufacturer or the device vendor. Where we start getting into the device certificate chain is the device certificate CA, and then alias intermediate CA, and the alias certificate. And so correlating these with the OCP terms, the device certificate CA is the OCP identity key, and the alias certificate is the OCP attestation key. One of the ways of deriving these keys is known as DICE, and that's come up many times on the talks today. DICE uses secrets that are derived as part of the boot process, and then with DICE attestation, you can use those keys as seeds in order to derive public key pairs that can be used for attestation. So working through that flow from the bottom, an immutable ROM uses a unique device secret combined with the hash of the first mutable code to derive a CDI, a compound device identifier. And this is the secret that's wielded by the FMC or layer 0 firmware. The FMC, in turn, can then feed that CDI into a DRBG algorithm to come up with a device identity key pair. The same flow can be inductively applied to the second layer code. We call here the SMC or layer 1. And that can do the same process to derive an alias identity. And so the firmware layers end up mapping all the way up through the certificate chain. Now, as we go through implementing this, we've faced a variety of problems. And I'm going to pass the mic to Dhawal here to explain some of those problems and how we approach them.
Thank you, Varun, for the wonderful introduction on attestation and DICE, as well as SPDM. Now, clearly, at this point in time, the audience must be all set to hear what NVIDIA is doing about those. And some may be wondering, what even makes this talk interesting? Why is NVIDIA talking about it? And it's the why part that I want to begin with before I get into the what. And we express why as some challenges that we encountered when trying to implement DICE in NVIDIA platforms. The first is that of practical immutability of FMC. If you look at the picture on the right over here, it says FMC is immutable after manufacturing. The reason is that if it changes after secure manufacturing, then the certificate change ceases to be valid, and attestation would fall apart. And that wouldn't be good. Now, DICE very nicely moves some of the hard parts, such as X.509 certificate generation and the asymmetric key generation from RAM code into FMC. And that would be nice. That may give many vendors extra time to implement the FMC, make it more robust, but the point stands that it still can't be changed after manufacturing. Now, in many NVIDIA scenarios, the runway available between the time RAM is frozen and the time the secure manufacturing begins is just a short number of months. And RAM development may have started much sooner than FMC development. So even though the capability to push additional code into FMC is there, in practice, NVIDIA doesn't stand to exploit that capability in many scenarios. And obviously, if we don't perfect FMC, then we are left with a situation where we have to change it in the field, and that becomes a problem. Now, you might wonder, well, if NVIDIA can change the FMC during secure manufacturing, what if we transfer the burden to NVIDIA customers? And to understand how well that works, let's divide the NVIDIA customers into two different categories. One is the customers, data center customers, who may have elaborate managed deployments. They may have a clean room, they have a PKI infrastructure, they have HSM services, they may have a database that holds device unique data, which I'll explain why the requirement for in one of the upcoming slides. And all of that can be put together to support the need to change the FMC in the field. Note that even though if it is changed, it would at this point in time be tied to the customer PKI, not the NVIDIA root CA. Now, even if the customer is willing to do so, clearly this is operational burden for customers, and it takes time, which means if it needs to happen before the device is deployed, then it may lead to a longer time to market. If it is changed after the device has been deployed, then it will lead to potential downtime. But the second class of customers is the nasty one. Imagine a consumer class device. There, such infrastructure simply doesn't exist. And so it is infeasible to expect a customer to be able to change the certificate chain in the field. Even if they changed and we are trying to do remote attestation, it's not tied to the NVIDIA root CA anymore, and it still wouldn't be acceptable. Do note that NVIDIA ships the same architecture as well as implementation, or majority of the implementation, to multiple markets. And as such, it's important for NVIDIA to support all markets with the same approach. The second challenge that we ran into was increased boot latency. If you look at the picture on the right, what's happening with the advent of DICE is we slip in an additional layer, the DICE FMC in green. And ROM code is doing code authentication and all the secure boot checks, CDI generation, and FMC is doing nearly the same thing. It's just doing an extra step of X.509 certificate generation. But focusing on the authentication, which is typically done using asymmetric key, it's not a very fast process, usually slow. Even if it's just a few milliseconds in context of PCI devices, that matters. The next challenge is that of lack of an internal non-volatile storage on NVIDIA devices. And why is this relevant? It's relevant because typically secure manufacturing is done during the early stages of the manufacturing, and by the time the onboard storage is attached, it's just too late, and those facilities are much harder to secure. To understand that, let's look at the picture at the bottom, where on the left there's an NVIDIA GPU shown. It's coming out of the foundry. The next step is to do secure fusing or security-related fusing, like keys or security provisioning in general. And then for completeness sake, the picture shows an additional box, which is about the remainder of the fusing, remainder of the testing, not very relevant to this presentation. But the fourth box is the interesting one, As you can see, there are multiple instances of that box. What that's trying to show is that that is the place where the external SPI flash, for example, is attached onto the board. And that can happen at numerous contract manufacturers. In addition, it may not even be a facility that can be influenced by NVIDIA. For example, there could be add-in card partners who are building the board. So they are the ones selecting the flash, and NVIDIA is just providing the firmware. Clearly, putting NVIDIA HSMs and services in those facilities which NVIDIA has no control or no influence over is not going to be practically feasible. A recent technology has been to use secure recovery implemented in hardware to push the first mutable code to the device. And you might ask, well, sure, you may not have the mutable, you may not have the non-volatile storage, but what if you could push the DICE FMC through the recovery interface? And that's an excellent question. However, to understand why that does not necessarily fully work, let's look at the picture of flash or the non-volatile storage. If you look at items 1, 2, and other data on the right side, that's where I'm looking at right now. Number 1 is green. That can be handled by the recovery interface. Number 2 is red. That's the certificate, the device identity certificate. And it is device unique. It needs to be generated in secure manufacturing. Where do we store it if we don't have the storage? Now, you may imagine that, well, what if we could just save it into a database and push it into the non-volatile storage once the manufacturing is complete? That's a valid point. But again, consider the fact that there are multiple contract manufacturers as well as add-in card partners where NVIDIA doesn't have control. And again, that becomes infeasible to do. The last challenge is this more of a customer challenge, actually, which is related to what happens if the flash or the certificate in the flash is corrupted in the field. There could be multiple reasons. Some customers may be paranoid about supply chain attacks. They may just want to forcibly wipe the flash. There may be a malware that could have corrupted flash. There could be environmental conditions or just firmware bugs that could have led to flash corruption. So the picture on the bottom portion of the slide shows the workflow that NVIDIA customer would have to follow in order to bring the device back into a working condition in case a flash corruption were to happen. So looking from the beginning, on the left side, the flow shows the device ingestion workflow, where the operator in green in the middle is receiving the device. At that point in time, the operator is supposed to extract all the device unique certificates from the device, store into their database, and then deploy the device. At this point, device is healthy, green check mark. Some point in time, step 4 happens, flash corruption, and then the device is no longer very usable. This may lead to an alert to the data center operator, shown on the right-hand side of the picture. At this point in time, the operator is going to perform step 6, which is get the, first the operator will figure out which device is corrupted, then figure out the certificate for the device from their database and inject back to the device, and finally deploy the server back again. Clearly, this is a bit of a cumbersome process, and again, if you think of the consumer class devices, it becomes practically infeasible again. So with all the challenges covered, how is NVIDIA solving them? I'll highlight 2 key points, one which is covered in this slide and one in an upcoming slide. The key point number 1 is ROM issues the certificate instead of DICE FMC. Now, that obviously may raise many eyebrows as to, well, did NVIDIA put a lot of X.509 code, generation code in the ROM and make it more prone to security vulnerabilities? The answer is no, but we'll look at that in more detail in an upcoming slide. The second, and this first point addresses challenges number 1 and 2. The second key point is storage of the signature associated with the device identity certificate into OTP memory of the device, such as eFuse. Note that it is just the signature that's stored, not the entire certificate. If you look at ECDSA 384, the signature is twice 384 or 768 bits. For most NVIDIA devices, that's a bearable pain. For this slide, the picture on the right is very detailed. I don't want you to strain your eyes. Let's just look at the extreme right portion, which explains the main intent of the slide. So at the extreme right, you see hardware, immutable ROM, FMC, and firmware. This is just illustrative of one one of the flavors of firmware, the chain could have stopped at FMC itself, meaning many devices have just single layer of firmware. But in order to make it more interesting and show that NVIDIA's implementation supports multi-layer firmware, we show FMC and firmware as well. So in this picture, the hardware carries the device identity key and the certificate. Immutable RAM uses that to issue certificate to the FMC. FMC does the same for the firmware. Firmware in this case is also the root of trust for reporting. We are imagining a single CPU scenario, and as such there isn't a separate device, let's say like Calyptra, which is doing reporting separately. The certificate terms that we use in this context are device identity certificate, which is associated with the hardware or the immutable RAM. FMC corresponds to the alias intermediate certificate authority. Note that since there are 2 layers of firmware, FMC needs to wield the CA power or certificate authority power. However, if it was a single layer, it would not have been required. And then the FMC issues so-called alias certificate for the firmware. This slide gets into more details of the implementation. In the interest of time, I'll run through this very, very quickly. At the very bottom layer, at the very bottom portion of the slide, you see UDS, device identity.priv, and the certificate signature. It's not necessarily mandatory to store UDS and the device identity private key as separate items, but in the interest of keeping the boot latency low, we keep them separate. On the extreme right, on the right side, you see that UDS is used to derive CDI, which is to derive CDI2, the classic DICE workflow. On the left side, the device identity.priv, or the private key, is used by the immutable RAM to sign the alias intermediate certificate, which corresponds to the FMC. This certificate has the TCG DICE firmware ID, or DICE TCB info extension, which contains the measurement of the FMC. And that gives the assurance that first mutable code cannot lie about its identity. Now, on to the second key point, which is related to the storage of the signature in the fuses. How do we accomplish that? Certificates are usually variable length. There are lots and lots of fields. For example, serial number itself is a variable length field. And so how do we ensure that we can do all of this and just manage to store a signature in the fuses, as well as keep the X.509 complexity out of the boot RAM? Our approach is to use a templates-based mechanism, combined with certain tricks to ensure that most of the fields in the certificate, with the exception of the signature, are constant length. What that allows RAM code to do is convert a certificate template generated offline, convert it to dir format. This is all done offline. And dir format just becomes an array in the RAM code. And RAM code additionally holds several offsets of data that it needs to patch. These correspond to the data that RAM code may have generated at runtime, such as public key of the FMC, such as the serial number of the certificate, and the signature, of course. And by indexing into these offsets, RAM code is able to patch them and essentially construct the certificate. However, that's not entirely sufficient, because there is one last remaining piece about the signature, which is variable length. Since the signature is variable length, at runtime, RAM code calculates the signature, looks at its length, and then holds few additional offsets of various length fields in the certificate, which goes as updates to construct the final certificate. Thus, we avoid all X.509 code. There is no standard ASN1 library. The only ASN1 related code is the code related to adjustment of the length fields in the RAM code. And we back this up with formal coding in certain products. The RAM code is written in a language called Spark, which is a subset of Ada, and allows us to do formal verification. Formal verification allows us to guarantee properties such as lack of or absence of divide by 0, integer overflow, absence of integer overflow, absence of unintended, unsigned integer wraparound, buffer overflow, memory corruption, and more. And as mentioned previously, the signature is stored in the OTP and patched through a template mechanism. The last piece to also keep in mind is the building of the IK certificate. That is built using the firmware. It does not need to be built in ROM. So ROM constructs the certificate for the FMC, or alias intermediate certificate. And the RTR in the picture shown previously constructs the IK certificate using the signature from the OTP memory. With that, I'd like to hand back to Varun to take us to the finish line.
Thanks, Dhawal. And in the interest of time, we'll just move very quickly in terms of the manufacturing flexibility, in that OCP attestation supports two different forms of provisioning, one where in high volume manufacturing, the secrets can be injected, and another when they can be provisioned on device. And this architecture supports both modes. So this slide is showing the injection, where the high volume manufacturing flow and HSM is going to generate the device identity public-private key pairs, and it's going to generate the UDS. And then both of these are going to be wrapped with some form of fuse wrapping secret, and then provisioned to the tester, which will then inject into the device. And then these will be unwrapped on every boot. There's an alternative flow where the device may generate the UDS and device ID private key internally, and then only export the public key to the HSM through a certificate signing request. And this architecture would support that as well. It just complicates the manufacturing flow. And in terms of our usages, this design is being deployed now in terms of the H100 products, and we plan on spreading it through the NVIDIA product portfolio. And then lastly, in terms of the call to action, I think one area that we're actually working in the last couple of weeks is figuring out how to integrate these flows into Calyptra, so we can minimize the amount of OTP and simplify the provisioning flows. And we'd like to hear feedback from you and all the other partners at OCP. How does this proposal work for you? Have you faced similar challenges when it comes to implementing DICE? We'd love to hear from you. With that, we'll take it for questions.
Yeah, thanks for the presentation, really good. Yes, these challenges do exist. I have one question on the device certificate. Device certificate needs to follow the chain, and it needs to go out to the root CA. So if you keep the signature, the to be signed certificate part of it changes, the upper layer changes.
Right. So
the issuer of the device certificate gets compromised, and if he recalls it, how do you manage that if you have put it in the OTP?
Yeah, and that is certainly one of the challenges we have to address. I think the area that may come there is in terms of renewability, where especially as technologies like Puff start to add, then you start to have the ability to provision more silicon identity keys. I think the area that you're pointing to is a real problem, because at some point you have to certify that chain. And so what we are doing is limiting the rationale that you need to bring a device back into a provisioning environment, but it doesn't entirely eliminate it.
So in that case, you consider the device itself as compromised? Okay.
Yes.
There is an additional point I want to add, which is currently not implemented, which may be the reason why Varun said what he said, which is this current workflow does not prohibit you from additionally provisioning additional certificates into the flash. If you look at SPDM, there are concepts of multiple slots, right? So this slot is only about the NVIDIA slot, and the other slots can continue to be provisioned, except that in such cases, the challenges number 3 and 4 will get back into the picture. Yeah. So it does not mean that the device is useless. It is supported, but it comes with that additional pain.
Yeah, you can either choose to endorse the device identity certificate, or you can choose to endorse the alias intermediate certificate, but they're trade-offs for both.
So you guys did the profiling, and you found that the generation of the key was taxing, or the signing was taxing? Just curious.
Signing is surely taxing. Generation also involves usage of DRBG, is less taxing. But in the slide, the area of tax I was alluding to was more related to authentication, where for PCI devices, incurring a few additional milliseconds is also considered a problem.
So when you say authentication, can you expand more on that?
Yeah, authentication meaning using a public key to authenticate the next layer of code.
Okay.
So if I slip in an additional layer of firmware, I have to authenticate this authenticates the next. So I added an additional step of authentication that previously did not exist.
Got it.
And you are absolutely right. The moment we were doing in certification, that also adds tax.
Yeah.
And the more layers we add, that also continues to go up.
Got it. Thank you.
Can you go back to the certificate template? So I noticed the serial number is not in here. How do you derive the serial number?
Wonderful question. Let me first list some of the other fields that are not shown in the slide. There's serial number, there's authority key identifier, there's subject key identifier. So we actually had looked at multiple specs and comply with them, TCG DICE, DMTF, PCI CMA, certain documents on Cerberus. And so all those exist. In terms of serial number, NVIDIA DICE already had a serial number and hence not shown in the slide, meaning even without all of this technology, we already had serial number. So the certificate for the device, which is device identity certificate, the same serial number is used in the certificate.
Okay, and the authority's key ID, that's hard-coded in ROM or?
No. So if you recall that the firmware, the root of trust for reporting, the topmost layer, is the one that's building the certificate, the device identity certificate, using the signature and a template. So ROM code does not even have to worry about that portion. It's the firmware that has to worry about it. And it's not hard-coded, it can be changed. There are more details about our implementation that we have skipped. So let me just throw out a potential choice up here. So imagine having multiple PCAs or provisioner CAs. Probably that's what you're alluding to, wherein I can provision using HSM1, provision using HSM2, and they correspond to different chains. Maybe they still go back to the same root CA, but they are different. And what happens in that case is the firmware holds multiple templates corresponding to the PCA used, and it uses that to build the certificate back again.
Okay, so there's additional fuses to identify.
Correct. It's more of an index. It's a very tiny fuse space, which PCA.
I see. So it's actually more than the signature fuses you need. You need additional fuses to identify which HSM it is signing, things like that.
Correct. Correct.
Yeah, I think if you look at the overall fuse list, it is the signature of the device identity certificate. It's any form of per device identifier, and then that index for a provisioner CA.
So we will have to take a break for lunch. Obviously, feel free to keep chatting, but we'll reconvene here at 12:30. But yeah, thank you guys.
Thank you very much.